The topic for today's video is atomic structure. Essential questions are: how did scientists develop our current model of the atom? So we'll be looking at atomic structure history and how these theories kind of evolved over time. We're going to start with the 1800s. There was some work done in ancient Greece with Democritus. He had an idea of having very small particles making up everything, but that's about as far as they got until the 1800s. So the first one we're going to talk about is John Dalton. He had the idea of atoms. He took that idea and he made it a little bit more specific. He said that elements are composed of tiny identical particles that couldn't be divided into anything smaller. Okay, J.J. Thomson is right here, and he actually discovered the electron. So John Dalton didn't really know about protons, neutrons, and electrons. He just thought atoms was it. J.J. Thomson started doing some research, and he discovered that there was an electron, or a negatively charged particle inside the atom. Okay, and he came up with what was called the plum pudding model of the atom. He thought, instead of having a nucleus, that the protons and the electrons were all just kind of mixed together. Plum pudding is a British dessert, and he's a British guy, and it's basically pudding with raisins all mixed throughout it. So that's what he thought an atom looked like. It just had the protons and electrons all mixed throughout it. Okay, so here's a picture of what that might look like. So all of the positive charge was there, and then electrons were just little dots randomly mixed in. Okay, so he was able to discover electrons using the cathode ray tube, and basically it is sending negative particles through, and it goes through a positive and negative applied field here in the middle. And so then he noticed that they all kind of were attracted to the positive side. So he knows that opposite charges attract and that the like charges repel. So protons and electrons should attract each other, and a proton next to another proton or an electron next to another electron should repel. Okay, and so this showed that there were electrons present. So we had this plum pudding model for a while that said everything was all mixed together. Then Ernest Rutherford came along, and he actually was looking to support J.J. Thomson's argument. He was going to do an experiment to help prove him correct, and this is what he looked like. And he did something called the gold foil experiment. So what this was is he had alpha particles, and he shot them in, and he figured that they would just shoot straight through. But what happened was that some of them, down in this region here, bounced back. And the only way they would do that, alpha particles are positive, the only way they could do that is if they hit another positive particle, because we know that positive and positive are going to repel each other. Okay, so all that positive is bouncing off. Okay, some did go through, but a lot bounced back. So what he realized was happening in this atom was that it was hitting a big section of positively charged material. Okay, so he figured out that actually they weren't all necessarily mixed together, that all the positive charges were in the middle, and they were small and dense, and that's why they were ricocheting off of there, is because of that. Okay, so, and he figured out the ones that were going through, most of the rest of the atom is empty space, and he still thought, like J.J. Thomson did, that the electrons were just kind of randomly in there. Okay, so then, after that happened, Niels Bohr came along, and he started doing some of the work with the electrons, and he came up with the planetary model of the atom, which is a picture that you see a lot. It looks like this, okay? So that looks kind of like the planets. They're on an orbit. Okay, so he wanted to figure out why they would stay in an orbit, and he determined that electrons can only be found in certain regions called energy levels. So it has to do with how much energy an electron had. So he did an atomic emission spectrum, which is basically they send through the energy, and it comes out in the form of light. And so this is the specific colors of light that come out of hydrogen, and each different element has specific colors of light that come out, a specific combination. So what an emission spectrum is, it's a series of lines that is unique to each element. It's kind of like we have fingerprints that are unique to us. Each element has a different set of lines. Okay, so that would be for iron. It has a lot more. It also has a lot more electrons. Okay, this would be for carbon, so a little bit fewer. And so what happens is they send the white light through the prism, and then it separates out into these different colors. So if it's if it's a specific element that it's going through, it's going to separate out to that specific element spectrum. Okay, so all the wavelengths of light are going through. And then if you have just a single element, okay, so this is sending hydrogen through, then you get just specific wavelengths. All right, so this is some of the technology that this allows. We can have fireworks because of this. The reason fireworks are different colors is because they're using different elements that send off different colors when they react. Okay, we can do a flame test, and we can see that different elements produce different colors of flame. So what does this all have to do with electrons? Well, the way they produce light is related to the electrons. So Bohr said that electrons only exist at specific energy levels. So like there's one and there's another one. And that atoms are able to absorb a definite amount of energy called a quantum. Okay, so what happens is that the electrons absorb that energy and they get excited. So they jump to a higher energy level, and a higher would be further away from the nucleus, and so it's going to be less stable. Okay, so it jumps away. And then when it falls back, it releases energy, and the way it releases energy is it shows light, and that's what your emission spectrum comes from. So it's falling back and releasing that light out. Okay, and so that goes out, and it goes back to what's called its ground state. So that's where its normal home is. And so all the electrons are in the lowest possible energy levels in ground state, which means the atom is more stable. Okay, so each line in the spectrum results from different electron transition. So like in the hydrogen, there was a red, and then there was a turquoise, and then there was a kind of purpley color. Those are coming from electrons jumping from different energy levels, different amounts. Okay, and they are not allowed to fall in between the energy levels. They have to fall that specific amount. Okay, so Bohr did all this work. However, it was discovered later that this really only works for hydrogen. It doesn't work as well for the other elements. So there has been developments after Bohr, and we will talk about that in one of our upcoming videos.